In game development, we use vectors to define meshes, directions, and all manner of other calculations, which makes them essential to understand. A vector is a line drawn between 2 points. Vectors also have a length, known as their magnitude. Let's start off by simply looking at 2D vectors. A 2D vector is a way of representing a point from the origin, the 0, 0 point on a graph, to any point on the 2D plane. Since it is from the origin, it has an implied direction. It's made up of two components, x and y. These represent the distance from 0 along the x and y in each axis. In this example, our vector goes from the origin to position 12, 5. The length of the distance between these points is called the magnitude. This can be worked out mathematically by using Pythagoras' theorem, which states that the square of the hypotenuse is equal to the sum of the squares on the other two sides. The hypotenuse in vector maths is the magnitude that we're trying to find. Imagine that there are two people in a field called Charles and Quentin, with a lethal vendetta. Being gentlemen, they've agreed to a pistol duel, but their guns only have a range of 12 units. So can they shoot one another? Let's find out. As you can see, the magnitude is the square root of the sum of the x and y positions on the grid squared, which when added together makes 169. The square root of 169 is 13, so Charles and Quentin will be unable to shoot one another, which is excellent, as violence has no place in this tutorial. Also, Charles totally had a crossbow the whole time. Let's look at another example of using vectors to solve a problem in 2D space. We've already learned that vectors can be used to denote a position in space relative to the origin point. But you should also know that a moving object has a velocity, a change in position over time. This can also be expressed as a vector. In this diagram, Frederick is at position 5, 6 and has a velocity of 12, 5 per hour. This means that he will travel in a direction that is 12 further in the x-axis and 5 further in the y-axis. So in order to find his new position after 1 hour, we'd add his current position vector to his velocity vector to discover where he will end up. 17, 11. Remember that all vectors are expressed relative to the origin, the 0 point in space, and this is no different for velocity vectors. In the same way that 5, 6 is a position relative to the 0 position, 12, 5 is a velocity relative to 0 motion. So whilst he may still have the same velocity, 17, 11 is Frederick's new position vector after 1 hour. This is useful in game development tasks that involve prediction. You should note that the components of the final position are equal to the sum of the components of the two vectors. 5 plus 12 is 17 in the x-axis, and 6 plus 5 is 11 in the y-axis. This also applies to subtraction. Three-dimensional vectors work the same as 2D, but extrapolated into the z-axis, which represents depth. The x and z axes make up a horizontal plane, and y is the direction that points up. Unity works on a left-handed coordinate system. This means that if you hold your left hand with your index finger pointed upwards and your thumb pointed out to form an L shape, and your middle finger pointing away from you, then the thumb represents the x-axis, the index finger the y-axis, and the middle finger the z-axis. This hand gesture can be helpful to remind you of the order of the axes x, y, and z. Given that z represents depth, in our previous example, Charles and Quentin would have actually been stood on the xz plane. Keeping in mind that any coordinates stated in 3D will be ordered x, y, z, Quentin would have been stood at 0, 0, 0, the 3D origin, and Charles at 12, 0, 5. To make things more three-dimensional, we could imagine that Charles was on a higher vantage point. Now stood upon his 7-unit tall podium, Charles is at position 12, 7, 5. The calculation to find the magnitude of the vector between Charles and Quentin is the same as in 2D, but now features the z-axis. Unity makes it easy to perform calculations like this with its helper function vector3.magnitude. See the documentation link below for more details. There are a couple of useful functions for 3D vectors, the dot and cross products. The dot product takes two vectors and produces a scalar, a single value, from them. To find the dot product of two vectors, we take their component parts, the x, y, and z values, and multiply them together to find the sum of the resultant values. This is expressed, for example, as ax times bx plus ay times by plus az times bz. With this product, you can find out information about the two vectors you've specified. One example of this is finding out whether the two vectors are perpendicular to one another. If the dot product of two vectors equals 0, the vectors are perpendicular. In this example, we have two vectors, a and b. Vector a is 0, 7, 1. b is 0, 0, 6. We can see in this example that the sum of the multiplied components is 6, which means that the vectors are not perpendicular. If vector a was 0, 7, 0, and b was 0, 0, 6, then we can see that the dot product equals 0, and the vectors are indeed perpendicular. Here is another example of using the dot product in this way. This time vector a is 4, 5, 11, and b is -3, -2, 2. Multiplying these components gives us -12, -10, 22, the sum of which is 0, so these two vectors are also perpendicular. An example of using the dot product could be when creating a flight simulator. You would check the world up vector with the forward vector of the plane. If the two were perpendicular, if the dot product equaled 0, then the plane should have the least amount of drag. As the dot product increases in a positive value, we would know that the plane is pulling up, and we could add more drag. If the dot product increases in negative values, we would know that the plane is in a dive. Unity has a helper function to perform dot product calculations easily. For details of this, see the documentation link below. The cross product is a different way of combining two vectors. Instead of producing a scalar, a single value, the cross product produces another vector, specifically a vector that is perpendicular to the original two. For example, if we took vector a and vector b and crossed them, then the product would be vector c, one that is perpendicular to a and b. This is mathematically denoted by the caret symbol, the up arrow shown here. Since Unity's coordinate system is left-handed, so is its cross product. Putting your left hand into the same pose as to determine the alignment of the axes, you can determine the direction of a cross product vector. In this example, your thumb and index finger represent vectors a and b, the known vectors, and your middle finger represents the cross product result, c. To look into the cross product in detail, we would arrange our vector a and b components like this. But how does it work mathematically? To work out the cross product, we'd place our two vectors next to each other, and then repeat this below. From here, we can combine the components one at a time to find the cross product. First, we multiply ay and bz. We then subtract az multiplied by by. This gives us the x component of the cross product. Next, we do the same with az and bx, and ax and bz, to give us the y component. Finally, we do the same again with ax and by, and ay and bx, to get the z component. The good news is that whilst this is a detailed calculation, Unity has another helper function to perform this for you. It looks like this. One example of using the cross product is finding the axis around which to apply torque in order to rotate a tank's turret. Given that you have the direction that the turret is currently facing, and the direction that it needs to face, you would cross these two vectors to find the axis around which to apply rotational torque.